Hi folks, welcome back on my YouTube video channel, and today we continue talking about the assumptions that we use in strength of material course and finite element analysis. We have already discussed two assumptions in the previous video, so you can click here to revise this video, but for now we go ahead. Today's first two assumptions we are going to talk about are related to each other. I advise you not to separate them. Imagine that they are as one big assumption, okay? It will help you not to be confused. Formally, these assumptions are considered separately, but they are covered with almost the same definitions, and these assumptions sound similarly. Okay, let's get started. The first assumption is: body is considered to be completely elastic if after unloading a body fully recovers its original shape and size. This assumption is valid only until the load within the limit of elasticity. And the second assumption is related to Hooke's law. Deformation of the material is directly proportional to the applied force, so this is a definition of a Hooke's law, and again, law is valid only until the load within the limit of proportionality. It seems you have already heard something like the second part of it, have you? So, what does it mean? To show it, I would like to use force deflection curve. As you see on the picture, we have a specimen. On both sides of it, the load is applied. While the specimen is being stretched, the elongation occurs. This elongation, delta B, is very small. Now I take my helper and show you how the Hooke's law looks. As it stated before, the increasing of load leads to increasing in length. It is truly only here, in linear elastic region. Different materials have different curves, but the meaning the same. One important thing is this coefficient K. This coefficient is a constant of proportionality, known as the spring constant, which is usually given in newtons divided by meters. In the most cases, scientists can calculate this characteristic of a material with this formula: K equal delta P divided by delta B. And look carefully, I take force and divide by area of this cross-section of our specimen. You see, we find out stresses in the cross-section. Okay, let's go further. I take this elongation of our specimen and divide it by whole original length the specimen had before loading. We have a strain. The second curve shows the same behavior, but here we added the point, yield strength. And as first assumption stated, after unloading, a body completely recovers its original shape and size. This assumption is valid only until the load within the limit of elasticity. And again, I take the helper, and you can see, as stresses is growing, the strain is growing proportionally to until this point, yield point. You can see the first part of curve is a straight line. Here the Hooke's law is applied. And that is why we have linear relationship between stress and strain. As you can see, these two assumptions may be confusing for you, but keep in mind that the first assumption derives from Hooke's law. Most materials have to follow these rules. In most cases, we are working with load and stresses that are in this elastic region. So why we do that? Firstly, because of linear relationship between stress and strain. Secondly, because it's more easier for us to solve problem. It's more easier to predict the behavior of a construction, and calculations go faster. We can go further in plastic region, but in this case the solving can be difficult because of non-linear relationship. Look at here. The stress increasing slower but in this time the strings go faster. All these depend on the material and conditions we work in. Thank you guys for watching me. Subscribe on my YouTube video channel, press the button, share it and like it. See you next time.